Hello friends, welcome to lecture series on matrix analysis with applications. In the last lecture we have seen that what linear transformations are and what are the fundamental properties of linear transformation. In this lecture we will see that what do you mean by rank and nullity of a linear transformation. Okay. So, let us start. Let V and W be vector spaces over the field F and let T from V to W be linear. Okay. Then basically what we are having a linear transformation T from V to W. V is a vector space, W is a vector space over the field F. Okay. Now, the null space of T of this linear transformation T are all those elements in V such that T of V equal to 0 of W. Okay. All those elements here, okay, which map to 0 of W, it may be 1 or it may be a set. Okay. This set is called null space of T, and the dimension and the range of T is defined as all those W in W such that TV is equals to W for V equals to V. I mean the image of this in W. The image of this in W will be the range of T. Okay. Now, if V is a finite dimensional vector space, then rank of T is a dimension of range of T denoted by small r T, and the nullity of D is a dimension of null space of T denoted by N T. We will later on show that this N T and R T are the subspaces of the vector spaces V and W respectively. So, they have the dimension. So, dimension of the null space of T will be is called nullity, and the dimension of range of T is called rank of T. Okay. Say we have this example and we have to find for this example null space of T and R T and R of T. So, what is the linear transformation here? So, the linear transformation here is R3 to R2 and it is given by T of x1, x2, x3 as x1 minus x2 and 2x3. Now, first we have to find null space of T. By definition, it is all these are all those V in V such that T of V equal to 0. Now, here it is all those x1, x2, x3 in R3, x2, x3 in R3 such that T of x1, x2, x3 is 0, 0, because this is image is in R2. So, these are all those x1, x2 in R3 such that now T of x1, x2, x3 is nothing but x1 minus x2 comma 2x3 and it is 0 comma 0. So, this is all those x1, x2, x3 in R3 such that x1 equal to x2 and 2x3 equal to 0, that means x3 equal to 0. So, this is simply all those x1, x1 because x1 and x2 are equal and x3 is 0 such that x1 belongs to R. So, this is all x1 times 1, 1, 0 such that x1 belongs to R. So, this is basically the null space of T, or we can say that it is equals to span of 1, 1, 0. Okay. Now, to find range of T are all those y1, y2 in R2 such that T of x1, x2, x3 okay, is y1, y2 for all x1, x2, x3 in, you see, for all x1, x2 in it is x2. Okay. So, we have to find out R of T of all y1, y2 in this R2 such that T of x1, x2, x3 is equals to y1, y2. Now, you can simply observe here that T of if you take T of y1 comma 0 comma y2 by 2, So, it is equal to y1 comma y2. You can simply observe here, it is y1 minus 0 is y1 and y2 by 2 into 2 is simply y2. So, that means if you take, that means for any y1 y2 here in W, which is R2, there exists a pre-image here in R3. That means this map is onto. This is an onto map, okay, and since this is an onto map, so the range of T is nothing but entire R2, okay, because any vector in R2, because if you have any vector y1 y2 in R2, there exists y1 comma 0 comma y2 by 2 in R3 such that T of this equal to this. So, if you take any y1 y2 here, so there exists a pre-image here in R3. So, that means range of T is the entire R2. Okay. Now, there are some basic properties. The first property is range of T is a subspace of W. Okay. Now, what we are considering here basically, T is a map, linear map from V to W over the field F. The first is range of T, which is defined as all those W in W such that T of V equal to W for V belongs to V. For all, I mean you vary V in V, and a collection of all those W in W will be a range of T, and we have to show that this is nothing but a subspace of W. So, how can we show that? You take let W1 and W2 in R2, and for subspace we have to show that alpha times W1 plus W2 is also in R2, and you take alpha in field. Okay. So, if these are in R2, this means there exists some V1 V2 in V such that T of V1 is W1 and T of V2 is W2. Okay. Now, if you take T of alpha V1 plus V2, so since a linear map, so it is T of alpha V1 plus V2, T of V2, which is alpha W1 plus W2 by this expression. So, what we have shown that there exists an element alpha V1 plus V2 whose image is alpha W1 plus W2, that this implies alpha W1 plus W2 belongs to W, because this element is in V, and we have shown that there exists an element in V whose image is alpha W1 plus W2. That means this is in RT by the definition of RT. So, this means this is in RT, yes. So, this implies RT is a subspace of W. Okay. The next is NT is a subspace of W, the nullity. How we can show this? Now, nullity of T are all those V in V such that TV equal to 0. So, again you take some V1 V2 in LT and alpha belongs to field, and we have to show that alpha V1 plus V2 also belongs to NT for NT to be a subspace. Now, this implies T of V1 is equal to T of V2 equal to 0. So, now take T of alpha V1 plus V2. Since T is a linear map, so it is alpha times T V1 plus T V2. So, it is alpha dot 0 plus 0, which is equal to 0. So, this implies alpha V1 plus V2 belongs to nullity of T, because this element is in V, and we have shown that T of this element equal to 0, and T of all those V in V whose image is 0 are in null space of T, or nullity of null space of T. So, we have shown that null space is a subspace of V. So, basically what we have shown that if we are having two subspaces V and W, and T is a linear map from any linear map from V to W, then nullity of, if this is a nullity of T, then this is not only a subset of this V, this is a subspace of this V. and the image of this V, if it is say here, which we are denoting by RT, which is so it is not only a subset of W, it is a subspace of W. The next is, if T is 1 to 1, T is 1 to 1 if and only if null space is a 0 subspace or a singleton set 0 of V. So, the proof is again simple, let us discuss. Now when we can say that T is 1 to 1, T is 1 to 1 means T of V1 equal to T of V2 should implies V1 equal to V2 for all V1 V2 in V. Okay. Now let us first take let T be 1 to 1, and we have to show that null space of T is a singleton 0 of V. Okay. Now T is 1 to 1, let V belongs to nullity of T. So if we have shown that V is nothing but 0 of V, then we have done. Okay. Now if this belongs to null space, that means T of V equal to 0. Now this implies T of V equal to T of 0, because we know that T of 0 maps with 0 only. Now since T is 1 to 1, and by this definition we can simply say that V equal to 0. So that this implies nullity of T is nothing but singleton 0 of V. Now the converse, let null space of T is a singleton 0, and we have to show that T is 1 to 1. So let T of V1 equal to T of V2, and we have to show that V1 equal to V2 for T to be 1 to 1. So this implies T of V1 minus T of V2 will be 0. You can add the additive inverse of T of V2 both the sides. Now this is equal to, we know that this is equal to T of V1 minus V2 equal to 0. This implies T of V1 minus V2 equal to T of 0. Okay, anyway, this is not required. Now T of V1 minus V2 equal to 0. So this implies V1 minus V2 is in the null space of T, and null space of T is a singleton 0 of V. So this implies V1 equal to V2. Okay. So so we have shown that T is 1 to 1 if and only if null space of T is a singleton 0 of V. The next result is, if the span of V1 V2 up to Vn equal to V, then the range of T is nothing but span of T of V1 T of V2 up to T of Vn. Again it is easy to show. You see here, span of V1 V2 up to Vn is equal to V, and we have to show that R of T is nothing but T of V1 and T of Vn, span of this. Okay. Now T of Vi's belongs to R to RT for all I. Okay, because T of Vi is simply the image of Vi. So by the definition of RT, the T of Vi will belongs to RT. Okay, and since RT is a subspace of W, so we can easily say that span of T of Vi, span of T of V1 and T of Vn will be definitely contained in RT, because RT is a subspace of W. So to show that this is equal to this, we have just to show that RT is a subset of span of T of V1 up to T of Vn. Now to show that this is a subset of this, take an arbitrary element in RT and try to show that it is also in the span of this set. So let some W belongs to RT. If W belongs to RT, this implies there exists some V belongs to V such that T of V is W. Okay. Now since this V is in V and V is capital V is equals to span of V1 V2 up to Vn, that means this V can be expressed as linear combination of element of this set. So since V belongs to V, this implies there exists alpha 1 alpha 2 up to alpha n belongs to field such that V will be equals to alpha 1 V1 plus alpha 2 V2 and so on up to alpha n Vn. Now T of V will be equal to, since T is linear, so it is alpha 1 T of V1 and so on alpha n T of Vn. That means belongs to span of T of V1 and so on up to T of Vn. And T of V is what? T of V is W. Okay. So, we have shown that this W belongs to span of this. That means RT is a subset of span of this. So, from these two results we can say that RT is equal to span of T of V1, T of V2 up to T of V. Now the next result is, if V is a finite dimensional vector space, then R of T, that is rank of T, is always less than equal to dimension of V. So, it is easy to show. You see in the from this, if these vectors are linearly independent. So, if these vectors are linearly independent, so and a span of equal to V, that means V is n dimensional. Okay. And from this result we know that RT is equal to span of this, but span of T of VI's may not be linearly independent. Okay. So, basically the dimension of this RT will be less than equal to dimension of this, that is dimension of V. Okay. The largest Li set is itself. If this is the whole set is Li, then this will be the basis of V. Okay. But the image of T of Vi's may not be linearly independent. There may be possible that some of the T of Vi's are linearly dependent. So, the dimension of this will be less than equal to dimension of V. If you have a counter example, say you are taking span of 1 0 and 0 1 as R2, it is V1, it is V2. Okay. Now, you can define the linear map as this, T of x1 x2 as say x1 plus x2 and say x1 plus x2 again. Now, T of 1 0 is simply 1 1 and again T of 0 1 is again 1 1. So, span of T of 1 0 and T of 0 1 is of course equal to RT by the definition, by the result, but that is simply span of 1 comma 1, because both the elements are same. So, dimension of this is less than equal to dimension of this, it can't be more than this. Now, the next result is the rank nullity theorem. It states that if V and W are two vector spaces of field F and let T from V to W be linear, if V is finite dimensional, then nullity of T plus rank of T is always equal to dimension of V. So, the result is very easy to show. Let us see the proof. We have to show that nullity of T plus rank of T is equal to dimension of V. Here T is from V to W. Okay. This we have to show. Now, let us consider that V1, V2 up to Vn be an ordered basis of NT, null space of T, let us suppose. Now, since it is a subspace of V, so we can always extend this basis to form the basis of V. It is a subspace of V and T is a subspace of V. So, we can always extend this subspace to form the basis of V. So, let us suppose the dimension of V is say P. Okay. Dimension of V is say P. So, extend the basis of NT to form basis of V. So, let us suppose this is a basis of V. Where of course P is greater than or equal to N. Now we have to show that now let us consider a set. say we consider set S, which is nothing but T of Vn plus 1, T of Vn plus 2, and so on up to T of Vp. Now, if we anyhow show that this is nothing but range of T, I mean this is nothing but a basis of range of T, then the dimension of this, then we have shown, because here nullity of T is n, okay, and say it is k and it is p, then k will be p minus n. And if anyhow we have shown that this set S is a basis of RT whose dimension is p minus n, that means we have shown. So, we have just to show now that this S is nothing but a basis of RT. So, the basis of RT, we have to show the two properties. Number 1, it is linearly independent, and number 2, span of this generates entire RT. So, first let us see the span of this. The span of this is T of Vn plus 1, T of Vn plus 2, and T of Vn, Vp. We know that if V equal to span of V1, V2 up to Vn, then RT is equals to span of T V1 up to T Vn. Okay. So, now here span of V1, V2 up to Vp is equals to V, because this is a basis of V. So, the span of T V1, T V2 up to T Vn, T Vn plus 1, and so on T Vp is equal to V. Now, since V1, V2, Vn are in Nt, so T of Vi up to n is 0. So, these all are 0. So, that means it is equal to T of Vn plus 1, T of Vn plus 2, and so on T of Vp, and that is equals to it is RT, and that is equal to RT. So, the first property we have shown that the span of this is nothing but span of RT, I mean is equal to RT, that is span of this generates entire RT. Now, the second thing we have to show that this set is linearly independent. So, take some linear combination of these elements. Put it equal to 0, and we have to show that all alpha i's from n plus 1 to p are 0. So, this implies T of alpha n plus 1 V n plus 1 and so on up to alpha p V p equal to 0, because T is linear. So, this implies alpha n plus 1 V n plus 1 and so on up to alpha p V p belongs to null space of T. And since it belongs to null space of T and the basis of null space of T is V1, V2 up to Vn. So, this element can be written as linear combination of element of basis of Nt. So, this implies alpha n plus 1 Vn plus 1 up to alpha n alpha p Vp will be beta 1 V1 and so on up to beta n Vn. So, this implies beta 1 V1 and so on up to beta n Vn minus alpha n plus 1 Vn plus 1 and so on minus alpha p Vp will be equal to 0. But this set V1, V2 up to Vp is the basis of V. So, it will be linearly independent. So, this implies beta i's are 0 from I from 1 to n, and alpha j's are 0 for j from n plus 1 to p. So, we have shown that alpha j's from j varying from n plus 1 to p are 0. This means this set is linearly independent. So, we have shown that this is linearly independent and the span of this is equal to R2. That means this is a basis of RT, and hence we have shown the result. Now, let us come to few problems based on this. State true or false with proper reason. The first one is no linear transformation from R5 to R2 R3 can be 1 to 1. Now, let us see whether it is true or false. So, for all these things we will apply rank nullity theorem. By the rank nullity theorem, you see here T is from R3 to R2, okay. It is from R3 to R2, oh sorry, yes, R5 to R3, it is from R5 to R3, okay. Let us write again, T is from R5 to R3. So, it is V and it is W. So, what is the dimension of V? Dimension of V is clearly 5. By the rank nullity, nullity of T plus rank of T will be equals to dimension of V, which is equals to 5. If this T is 1 to 1, we know that T is 1 to 1 if and only if nullity is 0. Nullity is 0 or null space contains the singleton set 0, singleton 0. So, if it is 1 to 1, if T is 1 to 1, then NT will be 0. So, this implies from here RT will be 5, which is not possible. Since the maximum dimension of RT, maximum value of RT is 3, W is a, RT is a subspace of W. So, its dimension cannot exceed the dimension of W, it is a subspace of W. So, RT is 5 here, which is not possible because the maximum value of RT is 3. So, no, we cannot have any linear transformation from R5 to R3 which is 1 to 1. So, the statement is false, statement is true, no linear transformation, So, the first statement is true. Now, second one, if T is from R2 to R2 is linear and 1 to 1, then it is onto. You see, here T is R2 to R2, it is V, it is W. So, what is dimension of V is 2, what is dimension of W is 2. If RT is, this T is onto means range of T will be entire W, then it is onto, or we can say that rank of T will be 2, rank of T will be 2 because rank of W, dimension of W is 2, okay. Now, it is given to us that it is 1 to 1, if it is 1 to 1 that means nullity of T is 0. By the rank nullity, nullity plus rank of T will be dimension of V which is 2, and 0 plus rank of T is equal to 2, this implies RT equal to 2, that means it is onto. So, yes, it is true. In the next one, if T is from R3 to R3 and it is linear and onto, then rank of T is equal to dimension of V. Here dimension of V is 3, okay. So, now it is linear and onto. Now, T is from R3 to R3, it is V, it is W, dimension of V here is 3, T is linear and onto. Onto means R of T is equal to dimension of W which is 3. So, nullity of T plus rank of T will be equal to dimension of V which is 3. So, what is given to us? It is given to us, it is onto. Now, here it is 1 to 1. So, it is 0 plus rank of T is equal to dimension of V. So, it is clear. So, in fact if U and V are of same dimensional vector space, here also in the second example also V and W are same dimensional vector space and T is linear. If it is linear and 1 1, it implies onto. If T is linear and onto, it implies 1 to 1, if it is same dimensional vector space. The next is if T is from V to W is linear and the finite dimensional, then rank of T is always less than or equals to minimum of dimension of V and dimension of W. You see, here T is the linear transformation from V to W, okay. Now, rank of now RT is definitely less than or equals to dimension of W, because RT is a subspace of W. If RT is a subspace of W, so its value will always be less than or equal to dimension of W. If it is onto, then it equality holds. Okay. And by the rank nullity, nullity of T plus rank of T equal to dimension of V. So, rank of T will be equal to dimension of V minus nullity, and nullity of T is greater than or equal to 0. It is 0 if T is 1 to 1. So, minus nullity of T will be less than or equal to 0, that means dimension of V minus nullity of T will be less than or equal to dimension of V. So, this implies RT is also less than or equal to dimension of V. So, since it is less than or equal to dimension of V and also less than or equal to dimension of W, so this implies RT will be less than or equal to minimum of dimension of V and dimension of W. Okay. The last one is, if T from R3 to R5 be a linear map, then RT can be a 2-dimensional subspace of R5. So, let us see. Now, here T is from R3 to R5. So, it is V, it is W. So, dimension of V is 3. Now, nullity of T plus RT is equal to dimension of V, which is 3. Okay. So, we have to see that there exists RT of 2-dimensional. So, yes, there exist. If it is 2 and nullity is 1 for some T, then 1 plus 2 is 3. Yes, there exist, but there cannot exist RT. I mean RT of more than 3-dimensional vector, more than 3-dimensional subspace of R5, because sum must be 3. The minimum value of NT is 0. So, definitely RT will be, RT is equal to 3 minus NT, and NT will be greater than or equal to 0, that means RT will be less than or equal to 3. It can't be more than 3. So, for this problem it is true. So, we have seen that what rank and nullity of a linear transformation is, and what are the few properties based on this. Okay. So, thank you.